To finish up the last section on sequences, we're going to do 7.5, which is called geometric sequences. The question is, what are the recursive and explicit formulas for geometric sequences? If you remember, we had another type of sequence, not called geometric. We had one called arithmetic. What's an arithmetic one? That's whenever you either add or subtract. And remember, we had that word constant difference. If you add or subtract a constant difference to the previous term. As an example, we could have something like 10, and then 20, and then 30, and then 40, and 50, and dot, dot, dot. So if you have a constant difference, that means you're either adding or subtracting the same amount. In this case, you'd be adding 10 every single time. So if that's addition and subtraction, you can probably guess what geometric is, just like we talked about geometric mean versus arithmetic mean. This is a sequence that is found by either doing multiplication or dividing the previous term by a constant. So as an example, we could say maybe we start with the number 8, and then we multiply it by 2. If we do that kind of rule, it would be 16, right? And you multiply that by 2, you get 32, and you get 64, you get 128, dot, 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 dot. So this would be a rule that if you're multiplying by a number or if you're dividing by a number. But remember, dividing is the same thing as multiplying if you just consider it a fraction. So when you say that you're, say, for instance, you're dividing by 2, that's the same thing as multiplying by 1/2. So really, you could just say the word multiplying here. It's the same thing as multiplying by fractions. However, with geometric sequences, instead of a constant difference, a geometric sequence has a different term. They call it a constant multiplier because you're multiplying one term to the next rather than calling it a constant difference. So for our first example, we're just going to go through and state what the constant multiplier is if there happens to be one. So for our first one, we're trying to figure out how do we go from 30 to 60, 60 to 120, and so on. So that would be pretty simple to think about, I think, which would be multiplying by 2. So we'll multiply by 2. If we go over to B, we have to kind of think of, well, how are we going to go from 243 to 81, 27, and so on? And since the numbers are getting smaller, it's like saying we're dividing by something. The only way for that to work is to divide by 3. 243 divided by 3 is 81. 81 divided by 3 is 27, and so on. Or you could also say it's multiplying by a third. So either one of these would be fine. But since we'll just go ahead and do an example with dividing, we'll say dividing by 3. Now sometimes you get ones that have decimals in it, and it may be more difficult to figure out how do you multiply one number to get to the next. So if you have no clue how it works, like how do you go from 2 to 3, and then 3 to 4.5, and then 6.75? One way to do this that is very, very easy is just to take the second term, 3, and divide it by the first term, 2. This, if you have a constant multiplier at all, if it's a geometric sequence, then this will be the same every time. So 3 divided by 2 is clearly what number? That would be 1.5. So if this happens and you want to check to see if it works, you can then take 1.5 and multiply each one of these to see if you get the next number. So for instance, if I did 6.75 and I multiplied it by 1.5, if you type that into a calculator, you should get the 10.125. So this one is multiply by 1.5. The last one is kind of a trickier one. You can see it goes from 3 to negative 12, so it looks like it's going down in value, but then it goes back up to 48, positive 48, and then it goes down to negative 192. So something weird's happening here where we're changing the sign every single time. The only way for that to happen is if we're multiplying or dividing by a negative number. So if you take 3 times a negative number, how do you get 12? That would be 4. And then if you do negative 12 times a negative 4, you get a positive 48. And if you do 48 times a negative 4, you go back to a negative. So you can have this cycle where it goes from positive, negative, if you include a negative number here. So we're multiplying this one by negative 4. It is possible to have negatives too. And again, if you use the method from before, it'd be negative 12 divided by 3, and that would give you your negative 4. All right, recursive formula for a geometric sequence. This one I think we kind of already know, we've already done, so shouldn't be anything too new. But here's like the correct notation for it. We're going to say the r is a non-zero constant. Let's consider your constant multiplier, which is going to be down here too. The sequence g defined by the recursive formula, so we're going to use g. That's going to be a curly bracket. We'll start at the top. We'll say g sub 1 just equals x, some number. And then the next line would be g sub n. Remember, this is recursive, so it has a curly bracket. Equals r, your constant multiplier, times g sub n minus 1. And don't forget the 4 integers part. So this is considered a geometric sequence. The first term is obviously your g sub 1, so it's equal to x, whatever number that is. And your constant multiplier is r in front. Also, remember what means previous term. That's what's sitting right in here, the g sub n minus 1. So this is how you do it with a recursive formula if we're talking about geometric sequences. You just multiply by the constant multiplier out front. For example, give the first 6 terms and the constant multiplier of the geometric sequence where g sub 1 is equal to 6. And then to get every term after that, you're going to take the previous term and multiply by 3. So this would be 6. We're trying to get 6 terms. So we're going to keep multiplying the previous number by 3. So you get 18. Then you would get 54. Then 162. I mean, 2 more. 486. And 1,458. There's the first 6 terms. And our constant multiplier, which I'll just label as r, would be 3. We're multiplying by 3. So we kind of already done this before. It's nothing new. So it shouldn't be a surprise as to how to do these ones with recursive. The new part will be whenever we get to do explicit. Write a recursive formula for the sequence 5, 12.5, 31.25, and so on. So we'll go ahead and use g again. Do g sub 1. First term is 5. Then we have to figure out what are we doing, what are we multiplying by. So I'll leave a little blank here. Do g sub n minus 1 for integers n is greater than 1. And so what are we multiplying by to get the next one? If you have no clue, again, you can cheat. Take 12.5 divided by 5 and see what that's going to be. It would be 2.5. Very helpful to know this little cheat instead of guessing how to get the next number, especially with decimals. And you can check the rest of them to make sure you get the decimal that comes after it. So we're multiplying by 2.5. And that's your recursive formula. Before we do our next one, which is a word problem, there's a little text that I took from the book that we'll just read through. So for explicit formulas and geometric sequences, which is what we're going to next. From the book, it says, you may have received a letter or email that promises good luck as long as you send the letter to 5 friends, asking each to forward it to 5 other friends, and so on. Such chain letters are illegal in the U.S. if the mailer asks for money. Sometimes they call that like a pyramid scheme. They send you something, they say send money to other people, and then send us money back, and the letters keep spreading, and apparently you're supposed to be making a lot of money, because if everybody does it and spreads it to 5 people, all this money will come back to you. It's illegal in the U.S. to do that. But we're going to do an example of this to create an explicit formula of what's going on and how many letters would be sent out. Part of the appeal of chain letters is that a very large number of people can receive them quickly. This is because the number of letters sent by each generation, so every single time you send out, it would be like another generation, of mailers forms a geometric sequence. The data at the right represent the first 5 generations to a chain letter in which a person sends an email to 12 people. So we'll get to the data in a second. Email to 12 people and ask each person receiving the email to forward it to 4 other friends. No person actually receives 2 letters. So we're going to say it keeps growing and new people keep getting new letters. So I basically just read through example 4. So we're going to try that by creating this pattern like we did last time with arithmetic sequences and see if we can figure out. So we'll fill in the table to come up with the explicit formula. So this would be the first generation, like your term number. We'll fill this out. It's 2, 3, 4, 5. And then we'll get a rule for the bottom for n. So the number of letters that are sent out at first would just be 12. Right? There's 12 people. And we want this to be forwarded to 4 other friends. So again, I'm going to write the pattern out a certain way, but I think what we might do is fill out this column first, and then I'll show you the pattern. So the next one would be 12 people, send it to 4 people. So that's just simply 12 times 4, which is 48. If this keeps happening, we're just going to keep multiplying this by 4. So you do it again, you get 192. Do it again, you get 768. And then we end up getting 3,072. So to do the pattern here, I'm going to show you how it works. We're going to just do 12 times 4, and in order to take care of these multiples of 4 that keep coming up, it's going to be 12 times 4 to the first power. And then on the next pattern here, we'd have 12 times 4, technically 2 times 4s, but instead of writing that, we'll write it as 4 squared. So this would be 16 times 12, and if you put that in the calculator, you would get 192. These equal each other. And if you keep continuing the pattern, it would be 12 times 4 to the third. You can check in the calculator, it gives you 768. And the last one would be 12 times 4 to the fourth. Check that one out yourself. That should give you 3,072. So the pattern here, much like the other one we did, these numbers all stay the same, the first 2 here, and we have multiplication between them, and the exponent is what's changing every time. So we'll at least have 12 times 4. The exponent and how it relates to the generation you're on, or the term number, again, is 1 less. So if you're on the term 2, we're putting in 1. If you're on term 3, you're putting in 2, and so on. So how that relates to the term n, it's always 1 less. So the exponent is going to be n minus 1. So we filled in the table to come up with explicit formula. So this is our g sub n. 12 times 4 to the n minus 1. And then we're going to find g sub 8. So it'll be 12 times 4 to the 8 minus 1. Of course, you can type that all into the calculator. If you're going to do it individually, you have to make sure you do the exponent first. So it'd be 4 to the 7th first, and then times 12. Obviously going to be a big number. So g sub 8 is equal to 196,608. And that would be your answer. So here's the general formula for it, which I think might be an obvious answer now. See how many more we have left here. So the explicit formula for a geometric sequence, in this geometric sequence G, with the first term being g sub 1, and we'll say we have a constant ratio r. By the way, this is the same thing as saying multiplier. Just so you're not confused, they use either word, they're the same thing. Here's our formula. It's g sub n equals, well, where does the number 12 keep coming from? That's your first term. So that'd be g sub 1. And then what are we multiplying by? The 4 keeps coming from our constant difference, or constant multiplier. To go from one to the next, we keep multiplying by 4. So that would be, in this case, we're saying it's r, the constant ratio. And then it has to be raised to the n minus 1. And this one also includes the 4 integers part, which I don't make you do that for the explicit one, only the recursive ones. One thing I want to notice, though, is that when n is equal to 1, what do you actually get here? So if you're trying to get your first term, it might be obvious what the first term is, but what happens here when you plug in 1 on both these parts here, and in for n, you would get g sub 1 equals g sub 1 times r to the 1 minus 1. You see what happens here? It's g sub 1 to the r to the 0. If you don't remember, anything to the 0 power is just the number 1. So we're just basically proving that you still get g sub 1. These two equal each other. So it does work. All right, on to example 5. So just real quick, though, the advantage to using explicit or recursive is that you don't need to write out all the terms, whereas with recursive, we kind of have to build on ourselves constantly with one term to the next. So for example 5, we're going to write the first, second, fifth, and sixth terms of sequence defined by this formula. If you notice, the multiplier here is -3. So we're going to be seeing this cycle of positive negative numbers. So a sub 1 would be 4 times -3 to the 1 minus 1. And again, this actually makes it 0. So our first term is going to be 4. Then we're going to do 2 and 5 and 6. So 2 would be -3 to the 2 minus 1, which is -12. And then we do 4 times -3, 3 minus 1, which is 36. Because that would be -3 squared, which is 9 times 4. And then 4 times -3, 4 minus 1. So that would be -27 times 4, which is -108. So that's how you do the first, second, fifth, and sixth terms. We kind of jumped around there a little bit. Example 6. We're going to create explicit formula for the following sequence. Then we'll find the 10th term of the sequence. So let's go back and use g again. We'll say g sub n is equal to, what do we need? Our first term. In case you don't remember, the formula goes like this. So we'll do g sub n equals our first term, which is 0.75. Then we're going to multiply that by the constant multiplier. Again, if you don't know, you could just divide them. If I do take 1.5 divided by 0.75, you end up getting 2. This is 2 to the n minus 1. Now that we have this, we can find the 10th term. So g sub 10 equals 0.75 times 2 to the 10 minus 1. So you're going to do 2 to the 9th power, which is 512. 0.75 times 512. And that is 384. So that's the 10th term. We have 2 examples left when we finish with this lesson. Example 7. The question is, are the following examples of geometric sequences? If so, write the explicit formula. So you're going to check and see if you can actually multiply one thing to the next to get each term there. And if I check those quickly, we should be multiplying by 6 every single time. So just see if 42 times 6 is the 252. And the last one, I think they all work. So we'll say g sub n equals our first term times our constant ratio, which is 6, and then to the n minus 1. And that's your formula. For the next one, if we check these ones out, how we go from 1 to 0.5, well, 0.5 divided by 1 is just 0.5. So basically what we're doing is we're multiplying by half or dividing by 2. So if that happens, we have to actually write this as a 1/2. So we have g sub n equals the first term, which is 1, times 1/2. That's to the n minus 1. And it should work for every single one of these. And for our last one, if we do 5 times what gives you 10, that'd be times 2. 10 times 2 is 20. 20 times 2 would be 40, not 25. So this is not geometric. It actually fails at the very last term they gave us. So there's some huddle problems to try. Three problems to try. And then we're going to move on to this one word problem after you try those ones. So the last thing we have to do is this word problem. So we'll read through that and try it. So it says, suppose a ball is dropped from a height of 10 meters and it bounces up to 80% of its previous height after each bounce. A bounce is counted when the ball hits the ground. Let h sub n be the maximum height of the ball after the nth bounce. So this was kind of weird, especially with this picture here. Even though they said it gets dropped at a height of 10 meters, that's not your h sub 1. In the picture here, it's measuring your h sub 1 after the first bounce. So you have the first bounce, and this height that reaches here, which we don't know, is our h sub 1. So we got to find out what that is first. And how do you do that? Well, if it bounces up to 80%, we have to figure out what's 80% of 10. So we'll do 10 times 0.8. Remember, move the decimal over 2 times. So this would be our h sub 1, which is just 8. So now we know that h sub 1 is 8. And we do know our constant multiplier because it's just what we keep multiplying by, 80%, which is 0.8. So this is going to be r, and then we have our h sub 1. So our explicit formula would be h sub n equals our first term, which is 8, times our constant ratio, 0.8 to the n minus 1. So that's the whole thing. And then for the rest of these, we don't have to find them all, but now we can figure out what the maximum height of the ball is after the 7th bounce by plugging 7 into those positions for n. So it's h sub 7 equals 8 times 0.8 to the 7 minus 1. So we do the 0.8 first to the power of 6. This is 8 times 0.262144. I'll use all the decimals. And then times that by 8. So you get about 2.097. This is measured in meters, so I'll use meters. So m. Or write out the word meters. And there is one word problem after this as well for you to try as a team mastery. But that is all 4 sequences. We did arithmetic, geometric, we did all the recursive and explicit, and then we are done doing anything new with sequences.